Welcome to lecture 4.3, where we're going to be discussing resonance for negative charges now. Now, this will be quite similar to positive charges with a couple key differences. So for the arrows, you'll notice that instead of using bond-to-bond arrows, we have this new system here. I'll say this is bond to atom and atom to bond. We're going to be alternating between these, and you'll see what I mean in a moment. Going back to the Canadian housing metaphor, the electron surplus is much more like what we see today, where a normal molecule has electrons, which are these little people, in every atom, which are the houses. In an electron surplus, we have too many electrons that we can't provide atoms or housing for. And what this is going to lead to is we're going to need to overload some of these houses. Right? Essentially, the idea here is that we're going to have negative charges, whether we like it or not. And we're going to, instead of having positive charges, we're going to be putting extra electrons onto atoms to make them negative. With that in mind, let's take a look at the allylic case once again. So allylic, to remind, means that we're going to be one away from an alkene, as we see here. This lone pair, this negative charged carbon, is one away from an alkene. Now, previously what we would have done for a positive charge was use a bond-to-bond arrow like this. The problem here is if we draw in the hydrogens, we can see that this original carbon with the lone pair was full. So there is no room to give even more electrons to that carbon. But if you think about it, it doesn't really make sense for us to move more electrons toward the lone pair. Instead, let's start from the lone pair and move from the carbon atom, this lone pair, to form a pi bond. So I could describe this orange arrow here as an atom to bond arrow. Now, this arrow by itself isn't going to be good enough. The reason for that is that this carbon in the middle had a full octet. We can't just give it more electrons. But this is where the concept of electron pushing comes in. We're going to be able to push these red pi bond electrons onto the first atom. So with these two electrons, these two arrows, the atom to bond and the bond to atom arrows, we're going to be able to draw this new resonance form with a lone pair on the first carbon and a pi bond between the second and third. So looking at these two forms, we can see a very similar hybrid coming. And that's going to look something like this, with a partial double bond across the molecule and a negative half charge on both sides. Again, the overall charge of the molecule is -1, but what we've done is we've delocalized the charge. Delocalization makes the molecule much more stable. So to be clear, when we draw this molecule, right, we're not typically going to be drawing these when we're doing chemistry. We draw a molecule like this, and someone trained in chemistry that has a strong basis on the fundamentals understands that this molecule doesn't really exist. It has another major resonance form, and these combine to make the true molecule, which is much more stable than either one of these would be. So this goes to show that resonance not only can stabilize positive charges, but is also fully able to stabilize negative charges as well. That is equally true in the benzylic case. So with benzene, we can do the same thing. We can start with our lone pair and go from the atom to the bond, making a double bond between those carbons, and then pushing this bond to this atom. Now you might say, well, what if I try to make a bond-to-bond arrow here? And this comes back to the idea of the electron surplus. We're going to eventually have to put this on an atom anyway. There's too many electrons in this molecule. So it's best practice to move right to the atom. This is going to put a lone pair on this carbon, and we can continue making resonance forms. Atom to bond, bond to atom. You can see that pattern with the arrows. Again, this is a pattern that you're only going to see with negatively charged molecules. The last one puts the negative charge on that carbon. And once again, we have 4 resonance forms. Now, Negative charges on carbon can be stabilized by resonance, but let's look at heteroatoms, atoms like oxygen and nitrogen, and see how they can complicate resonance.